Okay, well, thank you so much for inviting me. It's been a fantastic week so far, and I'm very happy to be able to give these 2 lectures on the joy of surfaceology, which is probably a word that I would say is maybe not familiar to most people in this room. Hopefully that will not be the case by the end of these few hours, hopefully not too many hours. So the goal of these 2 lectures is to precisely review this recent progress that has happened in trying to reformulate amplitudes in a few different theories as a problem about curves on surfaces. So that's where the word surfaceology comes from. So the goal is we'll start with a surface that specifies the order in the topological expansion that we're interested in study, and just by asking simple questions about the properties of the curves on the surface, we were able to define functions that ultimately define the respective amplitudes. So the first part of this talk will precisely be focusing on the formulation, this sort of formulation for a very simple theory of colored scalars called trace phi cube theory. So the Lagrangians here is just a very simple theory, or it is a simple kinetic term, and these scalars have a cubic interaction. They're colored scalars, so we should think of them as n by n matrices. Phi should be an n by n matrix. And so this new reformulation is actually closely related with a different way of thinking about string amplitudes. So in case you're here and you really like string amplitudes, hopefully you'll find some joy in this, just purely in this new way that we have about thinking about string amplitudes. That's one part of it. If you're here and you like string theory, but maybe you would also like to ask whether string theory is that unique, or is there something else that we could do? As I'll explain, this new formulation allows us to define a wider class of objects that in some particular limits contain string amplitudes, but that also let us define other things that are not literally string theory, but that at low energy still gives us a consistent description of the theory. So that's another aspect of it. If you don't care about string amplitudes at all and you just care about field theory amplitudes, then this new formulation will also give us a very nice way of extracting the low energy limit of these amplitudes, and from that formulate the amplitudes in a different way, but also conclude new features about these amplitudes. Okay, so the sort of key words that go into this new formulation are what are called U variables. So U variables are going to be the sort of main ingredient in building these sort of string amplitudes, and they will define what we'll call surface integrals, which are these integrals that we associate to each surface. And as we'll see, these variables are precisely built around making manifest features of amplitudes that we know very well, namely the location of the poles, as well as what happens near poles, namely that amplitudes factorize. But on top of that, it will let us sort of discover new features. One set of these correspond to new loci in kinematic space where these amplitudes vanish, so these are what we call the hidden zeros. And on top of that, other regions of kinematic space where now the amplitudes also factorize into products of lower point amplitudes, but where now this factorization is not near poles. So that's why we call them splits, okay? So these are 2 quite interesting features that I'll talk about later in my talk. So this is all the plan for the first part. On the second part, I'll explain how this formulation extends from these dumb toy model theory that probably most of us don't care that much about, but to theories that we care a little bit more about, namely to describe amplitudes of pions and gluons. And as we'll see, all the fascinating features that I'll describe in the first part will automatically generalize to these more interesting contexts. Okay, so let's start. So the first step in understanding this reformulation is to actually realize that already for this simple scalar theory, the sort of kinematical data that enters on the amplitudes are very nicely and simply connected with the information about curves on surfaces. So here I'm starting with a very simple example. For 4 points, we can sort of draw the momentum of the scalars entering in a 4-point amplitude tip to toe, so that they form a closed polygon like we see here. So I could think that this arrow is giving me P1, here I have P2, P3, and P4. Right, so this is just the sort of 4 momentum that enter in this case. And now this is what we call the momentum polygon. And now I can label all the possible cubic diagrams that enter at tree level for this 4-point amplitude by considering all the possible ways of triangulating this square. Okay, where triangulating just means dividing this polygon into triangles. So, for example, there are 2 ways in which I can do this. One is by drawing this curve 1, 3, and the other one is by drawing curve 2, 4. And from a triangulation, I can draw the dual diagram just by drawing a cubic vertex inside each triangle. So as follows. Okay? Oh, yes. Okay. Okay, so here are my two. So if we see these first diagrams, okay, so particles 1 and 2 interact. So to this term, I would associate a factor of 1 over P1 plus P2 squared, which is just the momentum flowing through the propagator square. And to this one, I would have a factor of P2 plus P3 squared. Okay, so these are just the standard S channel and the T channel. Okay, but quite nicely, we see that the sort of variables that appear in the denominators are exactly equal to the length squared of the chords that enter in the triangulation. If you want, this chord is associated to the vector P1 plus P2. So its length squared is precisely P1 plus P2 squared, and similarly here, we have that this chord that goes from 2 to 4 is just P2 plus P3 squared, okay? So this naturally motivates that we could introduce what are called these planar variables, which in general will label chords in this momentum polygon that are precisely the sort of sums of adjacent momentum squared. As it turns out, these variables, well, the number of these variables is equal to the number of chords that exist in these polygons. This is this famous n times n minus 3 over 2 for an n-gon, and this is precisely equal to the dimensionality of kinematic space. So this means that these xij's actually form a basis of kinematic space, and it's a particularly useful basis because it encodes the location of the poles. Okay, so this trace phi cube theory will have poles when any of these xij's goes to 0. Okay, so which is the sum of adjacent momentum. So here I have another example at 5 points, where I already draw my 5 pentagons. And in this case, I can divide the pentagon into 3 different triangles by drawing these 2 chords, so which I will get a contribution to the amplitude of 1 over x13 times x14. But then I can keep on going just by kind of cyclically rotating this triangulation around to derive all the remaining 5 terms. Okay, so we see that at 5 points, the amplitude has 5 different terms, which are given by these 5 different triangulations. Okay, so far, so good. So now I just want to slightly abstract this picture of the momentum polygon into a surface. Okay, so in this case, so at true level, my surface would be a disk. At 5 points, I would have 5 points in the boundary. And now, exactly as chords inside this polygon, I can draw curves in this surface that go from mark point on the boundary to mark point on the boundary. If you want, you can think that inside the surface we can draw the sort of momentum polygon and then say that each boundary component of the disk will inherit the sort of momentum of the respective edge. And so this means that exactly as it happened for the momentum polygon to a given curve on the surface, say curve 1, 4, I can read off a kinematic invariant associated to it by, in this case, by homology, right? So this curve I can deform into, for example, this boundary curve, right? Whose momentum would be P1 plus P2 plus P3. And so I would say that to this curve I associate a kinematical variable x14, which is just the sum squared of the momentum that I can read off. Okay, so this map, just to set up the notation, is done by homology. And then precisely like we had before, if we consider a full triangulation of the disk, so here I have an example at 6 points just to show that we get more interesting graphs. We can draw the dual graph by drawing again a cubic vertex inside each triangle. And so in this case, for a particular triangulation, it maps to a standard Feynman diagram, and we get a contribution of just 1 over the product of the kinematic variables associated to the curves that enter on the triangulation. Okay, so nothing special. So in particular, from this perspective, I'll think about my amplitude as a sum over all the possible ways of triangulating the surface, where for each triangulation I get a factor of 1 over the product of the x's corresponding to the curves that enter on the triangulation. Okay, so this is the definition. And at true level, I would say that the most important feature of amplitudes is the fact that they factorize on poles, right? So at true level, amplitudes are rational functions and have this extra feature. And in general, in like amplitudes, namely as Yara reviewed on Monday, these factorization features ultimately one of the main guiding principles when we're looking for other sort of mathematical structures from which we can extract amplitudes. We always look for some space that has this feature. When we go on a particular limit, it will turn into lower products of lower versions of itself in some way, which is exactly what the amplitude does. So in this language, Well, we know that the amplitude has poles when any of the x's go to 0. So that means that in particular, if I send a given x associated to some curve on the surface to 0, and I take the residue, then the amplitude will precisely factorize into the product of the two lower amplitudes that are associated to the subsurfaces that I get when I cut via d squared.
When you triangulate, do you allow internal vertices or you don't?
Sorry, what do you mean? The vertices, yeah, I mean, they're, what do you mean, internal or external? Sorry?
Oh, the internal vertices for red curves.
Oh, the red curve, yeah, I mean, I'm just distinguishing the internal curves from the boundary curves, just because the boundary curves are all on shell automatically, right? They all have p squared equals to 0.
But the red curves are all chords. They don't have any vertex in the middle.
Oh, no, they don't. Sorry, that's what you're asking. Sorry, yeah, I understand. Yeah. I mean, in a second, we'll look at more interesting surfaces where there will be a puncture in the middle, so curves can end on the puncture. But for now, I'm just sticking to tree level, so the curves don't have any vertex.
Tree level, there are no internal vertices.
There are no internal vertices. There will be internal vertices, exactly. Sorry, I didn't understand. Yes. Okay, so...
On shell diagram, gives out internal points.
Sorry, what?
Do you consider on shell diagram it gives out internal points?
No. I mean, there are internal vertices that are at the level of the diagram, but the curves on the surface don't have any internal points. They can't end inside the surface. That's what I guess.
So it's basically a shell diagram.
Well, yeah. Look here. I have a diagram that has an internal vertex, right? If that's what you're asking. So this
He said on-shell diagram.
Oh, which we're not doing. Yes. At the moment, this is just standard, like the standard tree level amplitude, where, I mean, yeah, going on shell would be kind of taking residues on these particular poles. Okay, so this is literally just a way of relabeling cubic diagrams and rethinking of the kinematic invariance as associated to the curves on the surface. So far I've only talked about tree level, but now let's precisely proceed to loop level. So for most of this talk, I will focus at just tree level and one loop, but all of these ideas extend to the higher orders in the topological expansion. But so the surface that we associate with one loop is exactly the disk, with the difference that now we have a puncture in the middle, okay? And so exactly in the same way that we saw earlier, we can sort of label all the possible one-loop diagrams by considering all the possible triangulations of the disk. So in particular, maybe the most simple one is this one over here, which, as Hiroshi was just asking, now this is a case where I have curves that do end on the middle of the surface because there's a puncture. And in this case, this triangulation will just be dual to our standard sort of box diagram at 4 points, okay?
Sorry, what do you mean by puncture exactly?
Well, a puncture is just, we can think of it as a hole, right, where, I mean, so if you want, the sort of way I would draw the surface would just be, I mean, something that has a hole,
Okay.
but just some old sheet with a hole.
Okay.
That carries no momentum, if you want. That is important. That would be important to say. Yes, so this is just giving me planar contributions. If I had non-planar contributions, that puncture should be replaced with some internal boundary where particles could source from. But anyway, so I'm just going to consider this case. So this is a possible triangulation. Here I drew two other possible triangulations that kind of give us other sorts of contributions. For example, this one would be a contribution that would give us a tadpole diagram. And in this case, we would have a contribution that gives us what we usually call an external bubble. But this is just to point out that when I consider all the possible ways of triangulating the surface, I will get literally all the possible one-loop diagrams that I can draw.
So we think the number of vertex is related to the number of loop momentum?
Well, we're going to talk about loop momentum in just a second. Just give me...
You already have loop momentum.
I actually don't yet. I haven't, well, I have to tell you still how the curves map to the momentum. I've told you that here, and that's going to appear in like just 1 second. So before doing that, I mean, naively, the rule that I want to associate now at one loop is exactly what I did at tree level. I want to say that to each curve on the surface, I'm going to associate some kinematical variable, xij, where I and j are labeling the beginning and the end point. So for example here, I would say that this term should be equal to the product of xi P, where P is just telling me that these curves end on the puncture. Similarly here, I would have, a few curves. I'm going to call this curve x13, x31, and then I also have this interesting tadpole curve that I'm going to call x11, and so on. I have a few other curves that I would need. This one would be proportional to, would have a term proportional to this curve that I'm going to call x21. Anyway, so this is just to highlight, this is what so following exactly what I did at true level, this is what I will want to do, but now I need to tell you how these variables map to momenta, right? That's what, here we saw that this was done by homology, right? I could deform the curve. However, at one loop, precisely by the reason that Hirose was just mentioning, while at true level, it's enough for me to label the boundary components of the surface to assign momentum to all curves. This is no longer true at one loop, and that's precisely because I now have these sorts of curves which I can no longer deform into a boundary curve, right? So that means that in order to define a basis of homology, I need to assign momentum to one other curve in my surface, and in particular, so let's choose that to be this curve. So I'll say that this curve has some momentum L mu. That's precisely the loop momentum. And from the moment that I do that, now any other curve in the surface, I can read off again the momentum by homology, just like before. So in this case, I have that this curve can be deformed into this boundary curve together with this curve that I just assigned. So I would say that x4p is equal to p4 plus L squared. Okay? Also, precisely because the puncture carries no momentum, when I read off my kinematic invariance in this way, I will have that the sort of curves that I associate to these sort of tadpole variables that just go around the puncture. Since the puncture carries no momentum, I can deform it into a boundary, then automatically there will be assigned zero momentum, which precisely agrees what we expect from momentum conservation, because we know that these propagators, there's no momentum flowing through them. Similarly, the same thing holds for these curves that I just draw here, this x21, which is precisely dual to one of these propagators associated to an external bubble. By homology, this kinematic invariant is also set to 0. So this is the case for tadpoles and external bubbles. Okay? And on top of that, in these sorts of diagrams, this also means that the sort of kinematic variable associated to this curve will be the same as the kinematical variable associated to that curve. Okay, so even though these two curves are different by homotopy, I can't continuously deform one into the other. They're assigned the same momentum. Okay, so this just matches what we expect in momentum space. So there we would have that x31 should be equal to x13. Okay, so these two curves. Okay, so having this, I've explained how we can assign, we can sort of think as the kinematic invariance entering at both tree level amplitudes as well as one loop integrands as being naturally associated to curves on surfaces. And in both cases we're dealing with rational functions because the integrand is what we get before we loop integrate. So we would hope that in both cases this feature of factorization should hold. As I'll explain in a second, in general, precisely because of these cases where we have to throw away the tadpoles and the bubbles, the factorization directly for the integrand is a little bit more subtle. I'll get to that in a second. So for now, let's just go back to true level where we know that the amplitude satisfies this nice feature, that there's a locus where it factors into products of two lower point amplitudes. Okay, so what I want to tell you now is precisely a sort of space, a mathematical space that has exactly this feature. So as Yara mentioned on Monday, a lot of examples that we saw in amplitudes of this type correspond to some sort of geometry, some sort of polytope, where the sort of facet structure precisely describes these factorization features of the amplitude. However, what I'll be telling you about today is a slightly different space that has much more of an algebraic flavor to it. And is defined by what I call the U equations. So we have such a space for any surface that we specify. So the surface determines the order of the topological expansion that we want to study. And what we do is the following. So pick a surface and consider all the sort of sets of curves on the surface up to homotopy. Okay, so classes of curves that can be deformed into each other. And now to each curve on the surface, I'm going to associate a U variable. Okay, so UC. And then I demand that my UC satisfy this set of equations that tells me that if I pick the U2 curve of a curve and I sum the product over all the other curves on the surface of the U variable associated to these curves raised to the number of times that this curve C prime intersects C, this has to be equal to 1. Okay?
This looks very much like Prutka relation.
It's very much related. So if you think of the U,
Grassmannian somewhere.
yeah, I mean you can. Well, it's literally the reason why these relations are satisfied. So if you think of the U's as the cross ratios of the Zij's, then they literally turn into Prutka relations.
Oh, okay.
Anyway, but so yes, but so I don't want you to need to know any of that for what I'm going to say. So
This helps me.
yeah, no, for sure. But so if this didn't make sense for any of you, it's not important either. But so these are just a set of equations that I can in principle give to you. I don't know if you're in high school. And so I'm going to say I care about this space defined by these equations, and on top of that, I will also demand that the U variable associated to all the curves are all positive. Okay, so this is the space that I'll be studying. So automatically, the first thing you should ask is, naively, I have as many equations as variables, so the solution space of these equations could very well be a point, a set of discrete points. But as it turns out, the dimensionality of the solution space of these equations is actually equal to the dimension of the moduli space associated to the surface, or more precisely, actually, the Teichmüller space associated to the surface, or if you don't care about any of these words, it's just that the dimension will equal the number of propagators that enters on a diagram corresponding to the order in the topological expansion that S is specifying. Okay, so in particular, at tree level, the dimension, the space of solutions will have dimension n minus 3. Okay, so at 5 points it will be 2, which is exactly 2 curves. Okay, so this is my space, and now I wrote here some examples already. So for example, at 4 points, like there I don't have the disk, but I have the polygon, which is equivalent. I have only 2 curves, and there's a single U equation that tells me that U13 plus U24 has to be equal to 1. At 5 points, I'll have 5 different equations corresponding to the 5 different curves. So here I wrote just a few. So let's look at the second one. I have that U14, which is a variable associated to this curve, plus now the 2 curves that intersected are just U25 and U35. It has to be equal to 1. And so on. So at 6 points, I'm going to use this example over here. So I have U14, and now it's just the sum of all the product of the curves that cross it, which in this case are just 2,5, 2,6, 3,5, and 3,6, and so on. So these are the sort of equations.
So you have to prove that these are only non-trivial algebraic relations.
Yeah, you can prove this by finding explicit solutions, for example, like prove the dimensionality of the space in this way. So that's yes. Okay, so these are my equations, but now what I would like to point out is exactly how just this set of equations has this feature of factorization that I described. And so what happens is that just from these equations, I have that when I send a particular U to 0, so when I go to a boundary of the space, so let's look at this concrete example. Say I send U14 to 0, then automatically, before that let me point out something else, which is that, so since all the U's are positive, this equation tells me that a sum of positive things has to be equal to 1, so that means that all of the U's need to live between 0 and 1. Okay, so on top of that I actually have that the U's live between 0 and 1. Okay? So now let's ask what happens when a U goes to 0. So let's say U14 goes to 0. Then because they're all between 0 and 1, that means that automatically all the U's that enter in this product have to go to 1, so that they disappear. Okay, so that means that if I look at this picture, then the sort of U's corresponding to all the curves that cross it have to go to 1, so that the remaining U's that are free are precisely those associated to the curves that live exclusively on the left surface or exclusively on the right surface that survive when I factorize. And in particular, I wrote here the sort of U equations for those curves, and we can check that when we go on the locus where all of these U's go to 1, so these terms go to 1, anyway, so that the remaining U equations precisely turn into the U equations for the 2 4-point factors that I have left.
Perhaps you already mentioned, I missed it. Is there a relation between U and X?
And the X, the kinematical variables? No, they're like, at the moment not. They will play,
How do you read off U from these step. You explained as if we know the rule of how to understand.
No, so at the moment I'm saying I'm associating a U to each curve on the surface, and I am observing that when the U associated to a particular curve on the surface goes to 0, this thing happens to the space. In fact, and I'm sorry, it's just an interpretation, right? I'm just saying that.
I'm not, if I don't understand your derivation, I don't have to worry.
Well, so far it's just a.
These are like worldsheet variables, and the x's are like target space variables.
Well, but that is not important even now. I'm just pointing out a feature of the space. Like the x's are the kinematic invariants but I'm just saying that the space itself has this feature. So in the moment, I'll explain how we can use the feature of the space to define a function that will have the same feature on the kinematic space. But at the moment, you could just know about these equations and realize that as a space, it has this feature, meaning as just a purely mathematical space. You can see that when a u goes to 0, all of the other u's go to 1, so that the space itself kind of factorizes literally into the space that kind of describe a lower surface that only has curves 1, 3, and 2, 4, and the other lower surface that only has curves 1, 5, and 4, 6, which are the ones on this side. So at the moment, I haven't told you any explicit connection between the u's and the x's, and they are not related. They will interplay with each other when I write down an amplitude. But at the moment, I'm just motivating these equations as by themselves knowing about the feature of factorization. Well, at the moment, the u's can just be defined as these equations. I don't need anything more. Right?
So far, u is just like
it's defining a variety. Exactly. It's an algebraic variety. And I'm just pointing out that just by the knowledge of these equations, we can tell that this variety has some avatar of this feature. When I go on a boundary, the variety itself factors into sort of lower versions of itself. So that's the only point that I'm mentioning. But now what I want to do is use the feature of the variety to build a function that will have this feature on some particular locations. Okay, so let's. Yes.
When the variable goes to 1.
To 0.
When 1 goes to 0, the intercepting 1 goes to 1.
Everyone else goes to 1, so they get fixed, and so the remaining degrees of freedom. And exactly. The sort of U equations precisely turn into the U equations of the two 4-point problems separately. So that's all that I mean. Exactly. Okay, so now just knowing this behavior, we can start playing around and say, let's build a function made out of these variables without going back to the x's that has this factorizing property. So the dumbest thing we could do, so let's build what I'm going to call a factorizing function. So the simplest thing one can do is just take a product over all the curves on the surface of their u variables. Oh my god. Sorry. Okay. So if we do this, then in this product, when a u associated to some curve x goes to 0, so pick some, x is a bad name for the complaint, so let me say some curve c prime. When a particular curve c prime goes to 0, if I factor out the u that is going to 0, okay, then the remaining product I evaluate on the locus where this u is going to 0, and precisely by this binary behavior, the contributions from all the curves that cross it are going to go to 1, so that I get so that this product itself sort of factors into the u's that live on this left surface times those that live on this right surface. Okay, so anyway, this is just schematic. Okay? And so now, I can do this like this, but now I can sort of try to say, but if I want to connect this to an amplitude, I should start introducing the kinematical variables, which is what the amplitude depends on. And so one simple thing I can do to this function that won't ruin this factorization feature is by sort of saying that to each u associated to a curve, I now raise it to some power xc. Okay, so that, this function will still factorize. And now this is literally, now I'm like just one step away from literally building an amplitude. The only thing that I need to do, so this is what I'm going to do here, is I'm going to define an amplitude as being the integral over this space. Okay, so I integrate over the space defined by these u equations for a particular surface. Well, the integration measure is some form in some variables that are called y's, which I'll explain in a second. So I'll have some integration measure And now I'll take literally the factorizing function that I just described. So I'll take the product over all the curves on the surface of their u variables. So now these u's are going to be functions of the y's. And then I raise it to an exponent, which just by unit should be alpha prime times the kinematic invariant that I associate to each curve.
So should I think of u actually as a Feynman parameter?
Yes, it's close. Yeah, I mean, it's closely related with the it's a Feynman parameter, exactly. Either the log u would be the Feynman parameter, precisely. Yes. Yeah, so this is going to be important in a second, but so just to make clear, the reason why the u's are functions of the y's is just because the y's are kind of the variables that are parametrizing the space of solutions of these equations, which I'll tell you more in a second. Okay, so this is my integral, and so literally this integral that I have over here is actually precisely equal to the string amplitude in open bosonic string theory. Actually, it's not literally the amplitude in open bosonic string theory. The closest object related to this would be the tachyon amplitude in bosonic string theory. Here we're just performing a particular mass shift so that instead of having tachyons at low energies, now I have these cubic scalars at low energies. Okay, so the claim is that if I start with this object and I take the low energy limit where alpha prime x is really small, then this object gives me the sort of amplitudes in trace phi cube theory. And the reason why I can show that is because I can show that that it has all the cuts correct, right? I mean, it will factorize exactly as a cubic theory for the cuts. Okay, so this is just going to come as a consequence of this feature that I'll explain in a second. So here, before, let me just give you some actual examples. So I haven't explained how the u's depend on the y's, but here I wrote this actual expressions. So here's an example at 4 points. So u13 is a function of the y's. It takes this form. Here would be the result for u24. Okay, and we can see that the sort of integration measure is a very simple logarithmic form in these y's. And this integral precisely evaluates the famous beta function in x13 and x24. Okay, so this is our S and T, which we're now just relabeling as the chords of the momentum polygon. Okay, so this is the function that we all know. It's represented in a very different way than the standard sort of worldsheet representation, but that's the whole point of the story. And this is very important at higher points. Okay, so here's another example. At 5 points, it's slightly more intricate. So we see the integral has dimension 2, so two-dimensional integral, which is exactly the sort of dimensionality of the space defined by these u equations, n minus 3, so 2 in this case. We have 5 different u variables. Here they're parametrized in terms of the y's. And you can go home, if you want, and check that these precisely satisfy these equations. So that's the sort of non-trivial part. Okay. But now what I want to emphasize is explain how, by putting this function under an integral, we've managed to turn the feature of the space into a feature of the function, which is now the amplitude. So what happens is that, let's look at this example concretely. So if I set x13 to 0, okay, then what's going to happen is that this term is going to disappear, and so my integral will develop a singularity in the region where y13 goes to 0. Okay? So when x13 goes to 0, the integral will be dominated by the region where y13 goes to 0, which is precisely the locus where u13 is going to 0. And so since these u's live on the support of the u equations, we know that on this locus, so u13 is going to 0, so we have that u24 and u25 both go to 1, and so that will mean that automatically this integral will factorize, because the contributions from the curves that cross it will go to 1. In this case, a very simple factorization because that's 5 points. But in general, what happens is that when I put a particular x to 0, the integral will develop a singularity in one of the boundaries of the integration domain that precisely corresponds to the region where the respective u goes to 0. And then from the u equations, we have that everything will factorize just by construction, because the contributions from all those that cross it go to 1, so that the integral itself factorizes. This product will automatically factorize. Okay, so this ends the discussion at the part at tree level. I'll get back to this parameterization in terms of the y's in a second, but let me now proceed to the sort of generalization to one loop. Okay, so we've talked about how at one loop we also have that the curves on the surface encode the kinematics. But so to generalize this object to one loop, all that we do is exactly the same. The only difference is that now the surface, instead of being a disk, is now going to be the punctured disk. And so we have the same sort of integration measure. We take the product over all the curves on the surface of their u variables raised to this exponent being alpha prime times the kinematic invariant that we associate to the curve. Okay? So just to sort of connect, so in this particular representation, this integral is basically ultimately putting all the diagrams together so that this is defining at low energies the loop integrand, but precisely because the dependence on the loop momentum only enters via the exponents, it's a little bit like, I mean, it's literally our familiar sort of Schrödinger parametrization, if you want. So we can trivially perform the loop integrals. Well, it's not literally the familiar Schrödinger parametrization just because it's taking care of all the diagrams at once. We usually do Schrödinger parametrization for one diagram at a time. So in a sense, this is defining something more like a global Schrödinger parametrization where we're doing it for all the diagrams simultaneously. Okay? So this is the idea. So this is defining the integrand, but we can perform the loop integrations easily just because of this fact. But so now I would like to point out a few differences between the one loop definition at tree level. The first one is that already at one loop, we start having curves on the surface that look like this. Right? So that means that these two curves intersect each other twice. So that's the reason why in these U equations that I defined earlier, these exponents have these intersection numbers. At tree level, these were only zeros or ones, but at one loop, they're now more interesting exponents. Okay? So that's one feature. But then the second one, which is quite dramatic, is that from the moment that I have a puncture, actually now the number of curves that I have on my surface is infinite. And the reason is very simple. First of all, is because to any curve that I can draw like this from I to j, I also have a corresponding curve which kind of loops around the puncture once and self-intersects itself. Okay? So out of this product, it's really natural to divide it into the contributions that come from curves that self-intersect 0 times, which are the sort of standard ones that I also use to sort of label the triangulations. So those like U0. Then there's a part that comes from curves that self-intersect any number of times. That's why I have an infinite number of them, because I can consider ones that self-intersects once, twice, and an infinite number of times. So this product over here is a genuine infinite product, okay? And then finally, at loop level, there's another sort of curve that I have on my surface, which is what's called a closed curve, that I'm going to call delta. Okay, so this is just a few differences. So this is U delta that has some exponent that I'm also going to call delta. I'll explain this in a second. But so the first thing that you can ask is first of all, this makes it clear that now this product is actually an infinite product. And this shouldn't be surprising, at least if we're claiming that we're defining string amplitudes, because we know that at loop level, we encounter all these complicated Jacobi theta functions that are infinite products. There are functions that are defined by infinite products. So this is like the sort of avatar of how we get that from this particular formulation. But maybe the first thing one can ask is, okay, but why do we need all these self-intersecting curves? I mean, they don't correspond, they're not curves that correspond to any particular sort of propagators. I can't build sort of triangulations of the surface using them. And this is actually important. So the fact that they're not they don't enter in diagrams means that actually they don't occur as poles in the answer. And the reason why this integral doesn't have any poles on them is actually very simple. If we just look at the U equations for these curves, precisely because they self-intersect themselves, then their U's are going to appear both in this term as well as in this term. And so that means that the U's corresponding to curves that self-intersect can never go to 0. Otherwise, these equations are not satisfied. So what this infinite product is really doing is just changing the UV. It's sort of, if you want, in string theory, we know the UV is very special, and this infinite product of curves is just contributing to change what happens at high energies. Okay, so there are no poles. So now you can ask, so when does this integral equal? Yes.
Is there only one delta curve, or are there an infinite number of delta type curves?
At one loop, you can define a single one. At higher loops, there will be much more. Yes. Yes. So.
is the difference between a curve which does not self-intersect itself and a curve which intersects itself plus this delta, or minus this delta.
Well, I can't do that, right? I mean, how can I, like, there's no sense, so what do you mean?
Can I not somehow deform it?
Well, the curves are, like, if they start and end at the boundary points, right, like, then there's two types of curves. Curves that start and end somewhere, which are these ones that I can kind of, yes, and then there's the curves that just end on the puncture, or these ones that don't start and end, and those are just these closed curves.
Deformations are not allowed. That's the game. It's the rule of the game.
Meaning, like, well, I can only deform them if they're, like, I mean, if I can continuously deform one into the other, yes.
But the intersection number is signed, so if you come and look like you're intersecting delta twice,
Well, but you can always draw them, like, so the intersection number is defined as the minimal number of intersections. You can move them around. So, for example, I could draw this curve as if it intersected delta twice, but there's always a motion that I can do that will have no intersection. So that's how you define the intersection numbers. Yes. Okay, so the question now is, when does this integral actually match the string amplitude? Okay, and as it turns out, there's a few kind of important features to match the string amplitude. The first thing is that it's crucial that you put all the curves, meaning all these infinite self-intersecting curves have to all be there. And also the sort of exponents that we associate to these curves have to be specially chosen. Okay, these ones are not, I mean, since they're not the standard curves, in principle you can assign them momentum in some particular way, these variables. So there's particular choice of these xq's and also the deltas that is required to match what you get from string theory. And in particular, for the remaining curves, they're all read by homology. So if I label these guys as x0, corresponding to the ones, these ones are just read by homology. Okay, so the rule that I just described to you. Okay, so this is the first, this is like the sort of thing if I want to get string theory. And the point that I want to emphasize here is that is a kind of a crucial difference between this way of formulating even the actual string theory amplitude, which is the following. I mean, while when I define the string amplitude in the standard way, where I kind of specify the momentum via like some vertex operators in the worldsheet, so that each sort of vertex operator carries a single momentum, then automatically, of course, the sort of momentum corresponding to the internal, these variables xc is just determined by momentum conservation. And so that will mean that we're forced to have that the sort of variables that are dual to the tadpole propagators have to be set to 0, and similarly for these external bubbles. And these, yes?
I guess the dimension, the actual dimension of the space hasn't entered anywhere, right? I mean, the dimension of the momenta p, for example.
Yeah, so far I'm assuming that my momentum live in d dimensions so that I don't have to care about any grand determinant constraints. So I will always assume that these x's are independent of each other. Yes, and that's going to be true. Okay, anyway, the point that I wanted to make is that if we read off, well, the momentum by momentum conservation, we're forced to set these guys to 0, and that's the only option we have in the standard picture, because we're inputting the momentum via, like, one at a time, by the momentum carried by each vertex operator. In this formulation, I can, of course, set these guys to 0, but I also have the freedom to keep them there. And what this is going to do is basically regulate a lot of the singularities that enter in string theory that usually you can't do in the standard way. Okay, we can put them back in. So it's obvious why, if I set x11 to 0, by the reason that we described, or like xii, the tadpole curve, this integral will develop a singularity when the respective u ii goes to 0, just by construction. That is not regulated because the exponent is non-zero. In the standard string theory picture, you don't have a way to regulate these divergences. You might try to do some sort of string field theory where you kind of look at the contribution of the moduli space that is giving you this diagram and try to regulate it. Here we have a completely much simpler way to regulate it, simply because we're inputting the kinematical data via the sort of curves rather than one momentum at a time. Okay, so this is naturally going to point me to one of the first generalizations that these formulations suggest, which is a purely kinematical generalization that will be important in the second part, that is called surface kinematics, where we'll see that instead of assigning momentum to each curve by homology, we can do other things, such that we basically define a bigger kinematical space where basically the kinematic invariants are now associated to curves. without needing to set these variables to 0. And this will be important in the second part to define integrands that have all the correct cuts, that factorize consistently on cuts. So this is one aspect of it. The second aspect is because, exactly as I was mentioning, the fact that there are no poles in these sort of self-intersecting curves, as it turns out, the contribution coming from this infinite product doesn't affect the low energy theory at all. So from this point of view, I can literally remove this product and say this integral is still a completely perfect way to sort of regulate my theory in the UV. Okay, it's not string theory, now it's something else. It will still have all the standard string theory features. First of all, it will have an infinite tower of massive states. It will be exponentially soft at high energies, fixed angle. It will have Regge behavior. It will have all of that. And in particular, it will also be unitary at all orders in alpha prime, because the massless cuts are completely unaffected, because all these curves don't contribute for the massless cuts. The only thing that this will change, and it's still an open question to understand, is whether the massive cuts are still consistent, whether this theory still is consistent at the massive levels. Okay, so this is kind of a generalization. So it's like where we take a finite product. But so if you want, from this perspective, we really have the freedom to dial how much stringy we want it. We can keep a few number of self-intersecting curves, all of them something in between, and at low energies, this all define perfectly consistent UV regularizations that are unitary at all orders in alpha prime, but that might have some problems in the sort of higher massive levels. Okay.
You're just looking at one loop.
This is at one loop.
If you get two loops,
If I get two loops, the surface, I mean, well, there are many, so you have a surface for each order in the topological expansion. If you have two loops, then the planar two-loop object will have two punctures. Now there are a few more features that you need to consider that arise at two loops. Well, you have all these infinite products, but on top of that, you now have this thing called the mapping class group that rotates the punctures around. Which,
my question was more, if you say you truncate your tower somehow at one loop, does that have implications for two loops?
oh, if you do a consistent truncation at two loops, then you will factorize the two loops into the one loop truncated. So, I mean, if you want to define it consistently at higher loops, you need to do similar things at higher loops.
You basically say that if my maximum loop, I'm looking at it, I have to do it consistently there, then it is correct for all loops.
For the remaining, yes.
I can not say anything about higher loop orders.
Yeah, I mean, here you don't, this is not going to have implications at higher loops. I mean, like, if you only care about, well, this guy, when you go on cuts, you will either find loop-level objects or tree-level objects, right?
Yeah, but you would like a theory which is consistent.
Yeah, so what I'm telling you, yes, exactly. And I'm just saying that you can definitely make something consistent, like also well, first of all, it's going to be consistent just because at low energies, it's literally like exactly what you would get. That low energy doesn't change at all. Like at low energies, everything is the same. That's, I guess, what I'm saying is that if you do an alpha prime expansion, well, first of all, the leading term is literally the same, and the other ones will all be consistent. And you can define the sort of higher loop generalizations in the same way. You can, again, sort of look and say, I'll only keep the curves on the surface that don't self-intersect. And this is something you can sort of do consistently. Okay, so that summarizes this first part. And now I'm going to, well, now this is a good point to make just sort of an historical remark. If David was here, he would correct me, because I think he's a big fan of these U variables, and as far as I can tell, the first actual paper that was written by Koba and Nielsen that tried to generalize the beta function for higher points was actually written precisely in terms of these U's. So it was something of that form. Okay. Then these variables were quickly dropped because the world cheap picture came along, and that picture made a lot of other features much more manifest. But these variables were very useful because they made the feature of factorization obvious, just as a consequence of those equations. Okay? So what has happened in the last few years is just that the sort of, well, at that time they only knew U variables for tree level, but now these U equations have been extended to all orders in the topological expansion, and in particular, this particular parametrization of the U's in terms of the Y's which is what I'll discuss now, was just introduced also in this series of papers by Nima and collaborators, well, in 2021 and 2022. Okay, so what I'll next sort of describe explicitly is this particular parameterization of the u's in terms of the y's. Okay, so this is what's called the positive parameterization, okay? It's called positive just because the y's are coordinates that range from 0 to plus infinity inside these integrals, as we can see here. Okay? So if you're a fan of string amplitudes and of worldsheet integrals, the first question you should ask is why are we reparametrizing them? And I think one of the main sort of deficits of the standard formulation in terms of the zij's is that you always need to gauge fix, right? Like this means you fix some of the z's, you use the worldsheet symmetry to fix some of the z's. And when you do this, what it means is that there are certain singularities that you can reach in the boundaries of the moduli space, and then you need to perform what are called blow-ups to sort of see what's exactly happening there. What this parameterization is going to do is precisely blow up all the singularities such that there's never any need to do these blow-ups. Okay? Okay, so what I'm going to give you is pretty much a recipe, because there's no way I could explain in any reasonable time where this parameterization comes from. But the first step is to sort of pick a triangulation of the surface, which ultimately, if you want, is like saying, let's define the surface via its dual Euler diagram. So for example, let's take this example at 5 points and consider this triangulation. So where I have curves 1, 3 and 1, 4. Then the dual graph in this case will be this graph, right? And I can just use the standard double line notation to represent this graph, since I'm dealing with a color theory, which would give me some graph like this, where I'm drawing it really fat because I'm going to need to draw a few more things. So this is my standard Euler diagram for that 5-point problem. And so you can think that this graph is completely equivalent to the disk with the marked points on the boundaries, because I can shrink these shaded regions into points, and then I get back precisely that surface. So the region inside this graph is completely equivalent to that surface. Okay, so and now the first thing that we want to do is, so this is defining our surface, and similarly at loop level, I also choose some triangulation, so some particular graph, and I can define my surface via this dual, what we call fat graph. Okay? So this is the first step. So that would be for the sort of box triangulation that I have there. So now the second crucial thing is that we want to be able to draw in this graph, the curves exactly the same way that we draw the curves on the disk. Okay, so and what we'll understand is that in terms of the fat graph, curves just correspond to sort of paths inside this graph. So let's do this explicitly. So for example, let's say that I want to draw a curve 1, 3, okay, in that fat graph. Well, as I drew it here, this curve starts and ends on a marked point, so it's not an obvious thing how I should draw it here. So to kind of go from a curve on the disk to a curve on the fat graph, I need to perform what's called the lamination. So this is just saying that to each curve, I consider its deformation clockwise, such that its endpoints, instead of literally ending on the marked points, which are nothing now, sort of start and end on these sort of boundary components. So in this way, I have that curve 1, 3 is the curve that starts between 1 and 2, and 3 and 4, so that I can now draw it easily here as a curve that starts in 1 and 2, and that ends in 3 and 4. Okay, so this would be curve x1, 3. Okay? So similarly, I can sort of draw, curve 2, 5. So now this diagram is getting a little bit more tricky by tilting, and so saying something that starts between 2 and 3 and ends between 5 and 1. So now let me draw it in red. So this would be 2 and 3 and sort of ends between 5 and 1. Okay? So this is like my curves on the disk are just recasted as paths on this fat graph. At loop level, exactly the same thing is true. there's this extra interesting feature that for these curves now that end on the puncture, if I want to define them as laminations, I can definitely tilt them here. But then it's not very obvious what I mean by kind of tilting near the puncture. So the only option is to think of this curve as some curve that spirals around forever around the puncture. Okay, so in particular, for this curve, I would find something that looks like this. Anyway, and it keeps on going forever. Okay, so there's the map between the curves on the surfaces and the curves on the fact graph. But now what I would like to do is find some way of encoding the information about the curves. And what I'll do is I'll literally just record the path that it takes inside the fact graph. So this defines what we call words. Okay, so this is just a way of encoding the information about the curves. So to do that, it's convenient to just label the roads or the edges of these fact graph, and I'll do it in this natural way where I'll just label a particular edge by the sort of two sets of adjacent roads. Okay? And so now I can sort of describe a curve by keeping track of its right and left turns at each intersection. So for example, for curve 1, 3, so let me call it like this, or for x13, what do I have? Well, this is a curve that starts in road 1, 2. So I'll write 1, 2. And when it reaches its first intersection, it turns right. Right, so I'll write right. Then it enters road 1, 3, which is this guy. And then in the next intersection, it turns left. So then I'll say, okay, this is left. Okay, so if we can do the same thing for curve 2, 5, which is the red curve, right? Then it starts in 2, 3. In the first intersection, it turns left into 1, 3. Then in the second intersection, it turns right into 1, 4. And then finally, it turns right again into 5, 1. Okay, so this is just a way of keeping track of what curves I mean, if I give you these words, then you can go back to your graph and sort of draw the path and you'll get the curve back. Okay, so it's just a way of recording the information about curves on the surface. And so the last point of this prescription is to tell you how to go from these words to the u variables of a curve. Okay, so those expressions that I derived there. So this last step is how to go from from words to the sort of u associated to a particular curve to the sort of u variable of the curve. Okay, so in particular, the way we parameterize the u's, so we saw here, for example, at 5 points, we saw that we wrote all of the u's in terms of two variables, y13 and y14. And as it turns out, the choice of the variables that our u's will be a function of is intimately related to the choice of the triangulation that we make in the beginning. So for this particular triangulation, I have two internal propagators that are 1, 3 and 1, 4. So my u's are going to be naturally associated to variables of these two internal chords. Okay, so these will be a function of the y's which are associated to the variables, to the propagators in the triangulation. Okay? So this is the last step. And so what I'll tell you now is just something that will look like black magic, but then I will spend 2 minutes trying to give you some intuition for it. But as it turns out, all of these sort of derivation and the understanding of this parameterization comes from a fairly abstract area in math, which is quiver representation theory. And so it would be extremely complicated for me to explain where all of this comes from. But I'll give you a simple intuition for where these ideas are coming from. Okay, but so let me tell you the black magic rule. So now I need my cheat sheet. So what I'm going to say is I'm going to define two matrices. One matrix is which is associated to turning left. So these are matrices of some y variables. And the matrix for turning left will be this one. And the matrix for turning right, because I always write these matrices wrong, so is this one. Okay, so these are just two matrices. In a second, I'll explain that they're kind of just, well, anyway, I'll explain in a second. So these are just two matrices, and what I'm going to do now is I pick a word, right, associated to a curve, and I take the products of these matrices according to the sort of right and left turns that I find in my word. Okay, so let's do this, for example, for 2, 5. right? So at the beginning, what I did is I turned left at row 2, 3. But now 2, 3 is literally a boundary road, so there's no y associated to it. The y's are naturally associated to the internal propagators. So that means that I just write, okay, I turn left, but then I evaluate this first matrix at 1. Okay? But then I turn right at 1, 3, so now I take the product of the matrix turning right. Now 1, 3 is associated with a y variable. And finally, I turn right again at 1, 4. Right? So this is just for 2, 5. So out of doing this, I'm just taking the product of 2 by 2 matrices. So in the end, I'm going to get a 2 by 2 matrix that will have 4 entries, A, B, C, D. Right? So these are going to be polynomials in these y's. And the claim is that the u variable associated to curve C is just going to be the ratio of BC over AD, whatever these polynomials are. And so if you do this for U25, for literally these, what we just did here, you should be able to find this particular expression over here. Okay, you should find precisely these ratio polynomials. Okay, so, well, there are a few sort of sanity checks that we can do to at least understand that we're doing, that this is not super wrong. First of all, we see that, so each of these matrices has determinant equal to y. Right, so that means that the product of the matrices that I find will be equal to the product of the y's, and the y's are positive, so that means that the determinant of these matrices is going to be positive, which means that AD is greater than BC, so that means that these ratios between 0 and 1, which is kind of what we expected from, like, we know that the u's all have to live between 0 and 1, so that's something. But now, I'll try to give you some intuition behind how this parametrization comes along. So one remarkable fact that, even if this didn't make any sense at all, should be surprising, is that I just gave you a procedure to build the u equation for a particular, yes, yeah?
Yes, so if the u goes to 1, then the determinant of that matrix is 0.
Yes.
Can you see it kind of immediately that it corresponds to the factorization?
No, u goes to 0 is when there's factorization.
Sorry, but the other ones, the u goes to 1 only if some other u goes to 0.
Yeah, but no, it's not always that. I mean, there's actually, u goes to 1 is not always, like, you can have, no, it's not always that. Yeah. Yeah. No, you can, well, at tree level, it is. You can always kind of map, but in general, it's not, I mean, the connection, there are many things that can explain a particular u going to 1. It's not like you're always, so it's that is not so easy. But so let me just make this point. So one thing which should be surprising is the fact that the procedure I just gave you, even if it seems like it comes from nowhere, is something that knows only about the information about a single curve, right? I mean, I can build the u variable just by knowing the information about what a curve, a single curve, does inside the fact graph, and somehow I am claiming that this parametrization is going to satisfy these equations which are much more global, which now know whether two curves intersect or not. So somehow with just the information about a single curve, I've managed to build a function that knows about whether this curve intersects other curves or not, because it satisfies these equations. Okay, so now let me tell you the sort of intuition. So from what I just said, this information about whether two curves intersect or not is actually quite important. I mean, that's ultimately how these u equations are being built. It's just taking into account that information. So one thing that we can ask is, how can we tell if two curves intersect? Of course, this is trivial by looking at them in the surface, but I would like to identify these by, like, the words rather than actually the curves. So in general, if two curves intersect, for sure there will have to be some period of time where they kind of do the same thing, I mean, inside the fact graph, right? And then eventually, after it, one of them kind of goes in one direction and the other one goes in the other direction. Right? And then maybe before, they started out doing something else. Okay, so this should be thought of as living inside this kind of complicated graph, right? I mean, anyways, this is just sort of schematically representing the path of two curves, like these ones over here. For example, the part where they do the same thing is just go through a particular road. So we see that for two curves to intersect, one of the curves have to have on its word that it turned left somewhere, then it did something, I don't know, I'm going to call W, and then it turned right again, right? So that's what this curve did. While for the red curve, it turned right instead first, and then it did exactly the same thing, and then it turned left again. Right? So for two curves to intersect, I must be able to find pieces of their words for which in one of them I have left something right, and then for the other one I have right, exactly the same something, and then left again. Okay, so this is the criterion for them to intersect. So now there's a natural counting problem that comes from this criterion, which is just say, well, it's natural for me to count all the possible sort of subwords inside a word that look like this, if I want to gather this information. So I define some function that counts or keeps track of all the number of subwords like that, and some other function that sort of counts all the subwords like this. Anyway, and as it turns out, the sort of u variable associated to a particular curve is going to be equal to 1 minus these counting functions f and g. Okay, so the point that I want to make with this is that this parameterization is really sort of answering a very simple counting problem about the sort of properties of the curves on the surface, which are ultimately related to how curves intersect each other. What these matrices are telling you is just a practical way of solving this counting problem. Okay, so this is all that I'm going to say about this counting problem. If you've ever heard this, maybe this sheds some light into things that you might have heard. If you've never, probably this didn't help at all, but so I'm sorry about that. Anyway, so, okay, so this is the end of the discussion about the particular way to write the u's in terms of the y. So following this rule, you can go home and like build these integrals for yourself. Okay, just this tells you exactly what these functions are.
Does this curve have to kind of explore the whole space like this red one does? In other words, if there was something branching off of 4, 5, you know?
Oh yeah, they can do whatever. So here I'm like saying, I mean, they do whatever before and after. What do you mean, sorry, explore the, no, in general, a curve.
I build the y variables for the 17-point case, and I have a fact graph that looks like this, but then there's
Keeps
a whole
range-
bunch of stuff that's
Yes, yes.
branched off there. Can I still use this red
You
curve?
can always, yeah, this red curve will be part of my surface. I mean, not all the curves will pass through all the y's, right? I mean, sorry, not all the curves will pass through all the roads, right? If
Can
you,
I still use that red curve for this much, for the y variables, for this much more complicated?
precisely, so if my exactly, so if my surface continued somewhere here,
Yeah.
this rule that I just described is exactly correct. There will just be more y variables associated to the remaining internal propagators that I would see in the rest of the fact graph that I would draw. But for this curve that still lives just inside this part, everything that I said still holds. Yes?
Question, couldn't curves intersect more than once?
That for sure, and that happens at loop level, not at tree level. Yes, but this thing will still hold. Like, I mean, but still to keep track of the number of intersections, you'll just see these patterns repeating. Like, you'll see like some combination like this, and maybe you'll see the sort of same feature but with a different W in the middle. So this criterion will still be true. That will just tell you that if you kept on going, exactly the same feature would happen. So that yes.
Up to the introduction of the two matrices, everything seemed symmetric and left and right.
Well, they're not literally symmetric, right? They're a little bit
Exactly,
different.
that's the question. Is there a simple explanation why you suddenly break the symmetry between left and right?
There is, and there's overall always a sort of breaking of the symmetry, and it's related already with what I told you about how to pick the laminations, right? I broke the symmetry by saying that for a given curve, I tilted right rather than tilting it left. So it's the same sort of breaking of the symmetry.
Sorry.
Yes?
So this foliation, is it necessary? Can you just identify the punctures of the boundary with the openings of the background?
So, sorry, what do you mean? I mean,
Here you have these shaded regions.
yeah, this is still, yeah,
It's one of those you identify with a dot on the boundary.
yeah, so this puncture you identify with this shrink of this point.
Yeah, and also on the outside, right?
Yeah, all around, like, so that would be, sorry, I didn't shade it here. Yes, everything is the same, yes.
So why can't you just, instead of associating the punctures on the boundary with those shaded regions, why can't you just associate them with the openings of the background? And then one curve that connects.
Well, because, well, the thing is that there's not a sense, so if I, there's not a sense where I cannot have curves end on these boundary regions, right? I don't know where to anchor
No,
them.
exactly. I mean, a curve that would, I mean, you don't
Well,
have
it's
to-
really because the fact graph is dual to like the sort of, if you draw the diagram which is dual to the surface, right, the legs are really dual to the boundary, which is what carries the momentum.
Right.
So that's the sense in which it's done. Okay, so now let me proceed. So far I've reviewed this formulation of the amplitudes, string amplitudes, and slightly beyond at loop level in terms of these U variables, which kind of are built around making manifest the feature of factorization, at least near poles, which is just a simple consequence of the equations that define them to begin with. So, okay, so far, at least the feature of factorization is kind of clear from this perspective. It's just a consequence of the equations. What I want to talk about now for the rest of this talk is this other property, which are called splits. Okay, so these are other loci in kinematic space where the amplitude will also factorize, which will be able to conclude as simple properties of these U variables again, but they have nothing to do with poles. Okay, so are different just places in kinematic space. And as it turns out, they arise from a very simple and natural question that we can ask. Okay, so take some surface that I'm going to define by drawing the dual graph, like I've been doing at the moment. I'll say some surface, so this is my surface S. And now, one natural thing is to say, well, consider some subsurface inside this surface. So let me specify this subsurface by drawing some. So this is my subsurface, let me call it S1. Okay? So it's a little bit like what Lance was saying just a second ago. I mean, it's just saying, I can think of this as a subsurface inside a much bigger fact graph, right? And now one question I can ask is, can I write the U variables associated to the curves of this subsurface in terms of the U's of the big surface? Okay, so can we write the U variables for S1, so that I'm going to call capital U just to distinguish 1. So these are the U variables of the subsurface S1 in terms of the U's in S, which are associated to the big surface S. Okay? Okay, so as it turns out, this answer has a very simple, this question has a very simple answer, which is as follows. So if you take a curve inside S1, so for example, let's say this curve, which kind of ends, it's just a curve that lives strictly inside S1, so let's call it some little x1, okay? Then the U variable for this little curve, little x1, can be written as the product over all the ways of extending this curve into curves in the big surface. So this I would write it, I'll take the product over all the curves x inside S, such that little x1 is contained inside x. Okay, so let me draw a picture that will make this clear. So I would say that the U variable for this curve is equal to the product over all of the U's that correspond to all the ways of extending this curve into curves on the big surface. Okay? Anyway, this one can simply derive from just the knowledge of the U equations as well as this sort of matrix rule that I just described to give the parametrization of the U's inside the Y's, but nothing better than an actual example to make this point manifest. So let me give the example here. So say that I take my surface to be a 5 point so that we can use those equations there. Okay, so, and let me consider my subsurface to be this 4-point subsurface. Okay, that would have indices 1, 2, 3, 4. Okay, right now, so in this case, if I look at curve 1, 3, right, this curve 1, 3 lives exclusively inside S1, so we have that the capital U13 is literally equal to the little U13, as the curve didn't change, so they both have the same U. On the other hand, if I consider the other curve inside S1, which would be 2, 4, right, this curve that ends there, now its U variable is equal to the product over all the ways of extending this curve into the big surface, which is just going to be, well, the ways of extending it would give me these two possible curves. So that would be U24 u2,5, right? As the curves on the big surface, this would be what we would call 2,4 and 2,5. Well, 2,5 we even drew there before. Okay, so now we see that this construction is correct because we have that, we should have that these capital U variables would satisfy the U equations for the subsurface, right? So since the subsurface is a 4-point, we should have that capital U13 plus capital U24 should be equal to 1, right? That's the sort of U equation for the subsurface. And that's exactly done automatically because when I sum this guy plus this guy, I precisely get back the U equation for U13 that I originally had for the 5-point surface. Okay? Okay, so this is what we call this extension formula that allows me to write the U variables for subsurfaces in terms of products of U variables for the big surface. Okay, so in particular, well now, of course, to this subsurface, I can associate a surface integral just like I did before. Right? I can say that the sort of integral that I associate with this amplitude associated to this subsurface is some integral with some logarithmic form in terms of the y's, where the y's now label the sort of propagators that enter in S1, which would just be this case. So this would be a one-dimensional integral, right, where I have the product of the capital U's in S1, right, labeled by these curves x1, raised to their kinematical variables, which I'll call little x's as well. Okay, so this is just saying that I can assign to each curve in the surface some kinematical variable x, and so there's some integral associated with this subsurface. And now I can consider another subsurface, which I'll choose to be this one. Okay, so let me call this subsurface S2, and I chose them to intersect on precisely a single vertex, which is a little bit of an odd choice. We're kind of used to the fact that we consider subsurfaces like in factorization and they don't overlap usually. But as I'll see, it's crucial that they overlap in a triangle. In a triangle meaning, in a vertex, in a cubic vertex. And to this subsurface, I can equally associate an integral, right? I mean, its surface integral, where now I have some form in, again, some y variables for the subsurface 2, which in this case would be associated to the propagators that are inside S2, which would be these two ones, right? And I'll take the product over all the curves in this S2 of their u variables that I'm now going to label with some w's, anyway, with their respective kinematics that I'm going to call w. Okay, so to each curve on that surface, I'll associate some kinematical variable. Okay, so far I didn't do anything. I'm just saying we can consider two surfaces, pick them to overlap on a cubic vertex, and then just write down the integrals that I'll associate to each of them. But now the crucial thing is that we can notice that if we take the product of these two integrals, we get back an integral that has precisely the correct dimensionality of the original integral, right? Because in the end, from here we would collect the dy over y associated to this propagator. From this form, we would have the dy over y associated to these two internal propagators, so that I'm left with, again, a three-dimensional integral, which is literally an integral over the original space. And on top of that, because I can write each of these u variables as products over the original u variables on the big surface, I can literally write this integral. So let me write it down over here. Actually, not over here, over here. But that will allow me in a second. So I can take these two integrals, and I can think of it as an integral over now the sort of final three-dimensional form in the sort of standard y. So in this case, it would be like dy over y cubed. Well, for the three different y's, so just schematically, there will be three of these guys. And then, by using the expression for the use of the big surface as products in terms of the use of by using the expressions of these capital U's as products over the use of the big surface, I can rewrite this product as a product over now the standard sort of Kober-Nielsen or like factor that we found over all the curves on S of their UC's, but where now the exponents will be linear combinations of these little x and little w, right? That I can just read off. So in the end, these exponents will have some sort of linear combination of little x and little w. Okay? So this is sort of each xc associated to a particular curve is mapped to some linear combination of these little x's and w's. And now what I want to tell you is just this map. Okay? So as it turns out, this map follows a very simple rule, which one can just easily derive from the extension formula that I gave you just a second ago. But just to write it, just take two surfaces that overlap. So this is 1 and this is 2. Now any curve on the big surface, so any curve on the big surface, x, right? So let's call this xc, or like, sorry, any curve c, let me speak precisely. Any curve c on the big surface has images on the smaller surface, right? As projections on the smaller surface, namely this blue curve inside surface 1 corresponds to this curve, while inside surface 2 would correspond to this curve. Anyway, this was a bad choice because this is actually a boundary curve, so maybe let me change my curve so that it's like this one, so that's a little bit more interesting. So let's say this curve instead. So a given curve sort of decomposes into curves on the two smaller surfaces, right, that I just described. And this mapping tells me that given this decomposition, I have that the kinematical variable that I associate to C maps into the sum of the sort of images of C in the small surface. So let me call this x1 and this w2. Okay, so in this case, I would have that x would go to x1 plus w2. Okay, so this is the map under which, when I do this for all the curves on the surface, so if this is what we call split kinematics. So if I start with my amplitude given by the surface integral associated to this big surface, and I evaluate it on these locus, so I do this map, that each xc is mapped in this way, then by construction I have that my integral will precisely factor into those two integrals, which are literally the sort of amplitude that I associate to the subsurface S1, which is depends on the kinematical variables little x, times that are associated with the kinematical variables little y. Okay? Anyway, so this, precisely because I chose my two surfaces to overlap on a triangle, all that this tells me is that all the curves in the big surface will be mapped to either a curve in S1 or in S2 or both, just like here. So this means that no x is going to be mapped to 0. So this makes manifest that the split is happening away from poles. Okay, so this is a different kinematical locus. So now I just want to do
in the factorization, standard factorization with the pole.
Yeah.
The sum of the two endpoints is like too different from that in the bigger one.
Yeah, it's exactly. So if you
How
want.
many is it here?
So, well, I don't know. So in the standard factorization, you're gluing surfaces together, right? By kind of gluing a leg, right? You see, the reason why, but when you glue this leg, the final object that you get, right? So I guess what I'm saying is the following. So the original integral, right? I mean, I guess the point is the following. So in this case, the sort of number of integrations for like, so the dimensionality of this lower point is like 1, right? It would be a one-dimensional integral. This guy would be a one-dimensional integral. So when I glue them together, I'm forming a new internal propagator. So the surface that I get would be of a one higher dimension. I can't literally take the product. That's why I need to take a residue, right? Like, I mean, when I start with a bigger thing, when I take a residue, I kill off one of the integration variables, and I get the product of two integrals that have the correct dimensionality. That's what factorization is gluing two surfaces, but when you glue this, you form a new internal road. That's precisely why in this case, on the other hand, this is the way that you have to glue two surfaces without forming any new internal roads. Okay? So that's the sense. So that's why we don't need to take any residue. Everything is just a particular kinematical subspace, which is what so the kinematical subspace is strictly speaking described by this map. But now I would like rephrase this map in terms of more sort of obvious or like a simpler way. So, and for that I'm just going to do this example, and then I'm going to finish because it's like 5 minutes to 3. So okay, so let me consider this to be my subsurface 1 and this to be my subsurface 2. Okay. So now there are 5 curves at 5 points, right? So I'm going to write them here. So x13 is the curve that we already draw there. And also here we saw that it just maps into a curve inside S1. So that will map to little x13. Then we have x14. Now is the curve that goes from here and ends there. So inside the red surface, it's actually a boundary curve. So let me draw that. So this is the curve. So inside the red surface is just a boundary curve. Inside the orange surface, it's curve that goes from 1 to 4. So that will be 1, 4. Then if we do the same thing for x24, then it would be, well, x24 is giving us little x24 plus inside this surface is giving us w14. Anyway, so now I'm going to do this a little bit faster, but you can. So now x25 inside the red surface again gives us little x24. Inside the orange surface, it is a boundary curve. So x25 is that curve there. Okay, so anyway, and then now this is going to end here. So x35 is also this curve, which now lives exclusively inside the orange part, which is w35. Okay, so this is the map. Like this is, I drew my 2 surfaces, I look at all the possible curves and I ask how do they decompose into curves on the subsurfaces, and I land on this map. Okay, so we see that this map is indeed imposing a restriction in the kinematics, which comes from this equation, right? What this equation is telling me is that I'm evaluating my 5-point amplitude on the locus where x24 is equal to x25 plus x35. Okay? Which is just the 2 other curves that I saw. As it turns out, this condition can be rephrased of setting a particular dot product between 2 non-adjacent momentum to 0, which is equivalent to saying that P1 dot P4 is equal to 0. Okay, so this should not be obvious, but you can check. So, of course, when P1 dot P4 is equal to 0, the amplitude has no pole because 1 and 4 are not next to each other. Okay? Anyway, so this is the locus, and the claim is that if you start with a 5-point amplitude and go on this locus, it factors into the product of these 2 4 points. And so I'm going to try to do this explicitly in these remaining few minutes. So if you remember from the beginning, we had that the 5-point amplitude was given by these terms where I summed over all the cyclic rotations of this triangulation. Right? So in particular, from the terms that have x24, multiply 1 over x14 plus 1 over x25. Anyway, and then I have the remaining terms. So I'm going to write here, sorry. 5, 2, 5, 3, 5. Anyway, so these are the sort of 5 terms, which here I decomposed in a particular way. But now I'm evaluating in this locus. Sorry, I think I messed up something. So I have x25 plus x14. Very important. Okay, right? So because w14 is x14. Other than that, I think this is correct. Okay, so then in this locus, we have that this guy goes to 1 over the sum, right? x25 plus x14. So that when I kind of reduce these 2 terms to a common denominator, from here, I just get a factor of 1 over x14, x25, right? That precisely combines with these 3 remaining terms into 2 terms that factorize to sort of give just 1 over x13 plus 1 over x, what is the other one? 25 times 1 over x14 plus 1 over x35. Okay? Anyway, this is just to show that you can actually see this explicitly. If you start with this point, you go on this locus, this turns into this sum, these 2 terms merge into a single one, and you get 4 terms that precisely split into literally the product of 2 4-point amplitudes. Okay, so this would be the 4-point factor that we associate to the red part, and this would be the 4-point factor that we associate to the orange part. Okay? So these are features that here I explain how they behave at the level of directly the field theory amplitude, but that are completely true at the level of the full string amplitude, and they're just a consequence of this feature of how the use of the subsurface can be written in terms of the use of the big surface. Okay, so these are what are called splits, and in general, if we explore all these possibilities of different ways of considering subsurfaces that overlap on cubic vertices, we'll find that there's some interesting collection of these pi's.pj's that we can set to 0 that will make the amplitudes factorize, okay, into lower point amplitudes, just like I did here. So from here, we're actually one step away to deriving locus where the amplitude vanishes just as follows. So consider some split pattern where one of the factors is a 4-point factor, right? Namely this one. Here I actually have two 4-point factors. Then I can get a 0 by further looking at one of these 4-point factors and setting their S and the T channel variables to add up to 0. Right? If I further go on the locus where x13 plus x25 is equal to 0, then this factor will vanish, and so I get a 0 rather than just a split. Okay, so in particular for these 5-point case, if I further set x13 plus x25 to 0, that would further set p1.p3 to 0. And so I would get that the amplitude would vanish when I send these two dot products to 0. Okay? So this is the point. This is finishing my discussion for this first part. I would just like to end with some comments. So first of all, using this procedure, we're able to derive a very wide variety of sort of collections of these non-planar dot products that we have to set to 0 to make the amplitude vanish, that are there at the level of the full string amplitudes as well as in the field theory limit, together with these interesting features of the places where the amplitude sort of factorizes for no apparent reason for it to factorize other than the explanation that comes from these rethinking in terms of these U variables. Okay, so just as a general point, I'm going to leave very soon, like tonight. But Justin is here for a while, and you can ask him on how just imposing literally these factorizations that I just told you, like just saying that just take any theory that you want and sort of turn it into sort of a bootstrap problem and say, well, I just want any theory. I want it to have these zeros that I described, and I also want the 5-point amplitude to factor into products of 4-point amplitudes, literally in the locus that I just described. You can ask for this at the level of the field theory answer, and it turns out these give you some constraints on the Wilson coefficients that are extremely restrictive and allow us to fully isolate string theory. So these are sort of naively properties that I just have very given to us. We could have understood them completely from the field theory perspective, but the most natural way to understand them is from these simple features of the U variables, and they turn out to be extremely constraining on the sort of possible space of theories. One more thing I would like to say is, so we saw, at this part I mainly reviewed how we can sort of reparameterize our string integral in terms of these U variables that make manifest the feature of factorization near poles obvious. And in particular, I explained this Y parameterization, which, as I briefly also mentioned, has this feature of blowing up all the singularities for us. In particular, this feature is very nice because it lets us extract the low energy limit of these integrals in a very efficient way. This is what's called tropicalization. So you can take these integrals and sort of tropicalize them to sort of pick up the leading contribution that happens when you go to low energies. And this then lends us on integrals that kind of unify all the diagrams and that describe the field theory amplitude in a different way. And so in this sense, so using these sort of tropical formulas, we can actually generalize this formulation to sort of build now amplitudes for any sort of colored Lagrangian that you give me. We can use these sort of integrals that come out of these low energy limits of this theory to sort of generalize it to other theories. But what I want to talk about in the second part of this talk is something a little bit more sort of magical, which is the following, is that, as it turns out, just by learning about these features that I just described, about the zeros and the splits, we can ask the question, take this family of integrals and do some sort of deformation. With a deformation, I literally mean a kinematical shift, but demand that this kinematical shift preserves all these features. So ask that whatever new amplitudes you're getting will still have all the zeros and the factorizations, And as it turns out, we'll land on a unique way to deform it, and this deformation is parameterized by some parameter, and when we change this parameter, what we'll get at low energies, that we'll find that instead of getting these colored scalars, we'll get pions and gluons. Okay, so that's what I'll explain in the second part. But precisely because this deformation is built in a way that preserves all the splits and the zeros, then what I just told you about are now also going to be features of pion amplitudes as well as gluon amplitudes. And they all have a very nice, they will have a very nice explanation in this way, but as far as I know, it's still very mysterious why all of these features are present there. So there are new, for the NLSM, we know about zeros coming from the sort of shift symmetry, the Adler zero, but we find a much broader class of zeros that hold for these theories. We can use the splits to derive multi-soft limits, and these are all features that we understand very naturally from this formulation, but that don't have a very obvious sort of standard picture. And I'll talk a little bit more about that, but hopefully this is just a summary of what I'll be talking about in the second part. Thank you so much for your attention.
Thanks a lot, Carolina. We have time for some questions. Maybe I'll start with it. So in the higher point case, the splits are always sort of codimension 1 constraints where you have one dot product set to 0?
No, in general there will be the codimension varies. Actually, when you go to higher points, you have different codimension constraints where the factorizations are different that you find. So the lower point factors that you find are different.
So you have to increase the codimension when you go to higher points?
Yeah, so for example, at 6 points, there's constraints of codimension 3, there's constraints of codimension 4, and at 7 points, there's constraints of codimension 4, 5, so there are different ones, but yeah, there's a...
And so maybe I don't know, if in the standard factorization, there's a difference between the sum of the number of legs of the two product amplitudes and the parent one, which is always 2.
Yeah, here's
4 plus 4. And I don't know if that rule...
It's different. Here you sum the number of legs of S1 and then subtract 3 because you're overcounting the ones inside this triangle.
Is that subtract 3 only for the 5-point case?
No, in general, because it's just...
Because it has to do with...
It has to do with this overlap on a cubic vertex, exactly.
Other questions? Yara?
So in some of the old string amplitudes papers from early 70s, they also had these string zeros, if you remember them.
Yes.
And some of the zeros are of the form like Sijk is 0, right? Like the free particle factorization. It's not the poles, but some other free particle.
Oh yeah, when you sort of get collections of these guys, then you can rephrase them as sums.
I wasn't sure. Yeah, that was my question. If you think that they are related to those or not? Yeah, because
I think they are literally if you're thinking about the same paper that I'm thinking, I think they are the same. Yes.
referees pointed at these papers.
What?
Some referees always.
Referees in your paper.
For
referees of somebody else.
There is a paper from 71, I think. Yeah.
Yes. So in those cases, they derived it in a very different way. I think here, the main emphasis is that, we can always sort of we can now understand them as kind of this last step after you split, right? The 0 is always associated with a split pattern where eventually you land on a 4-point factor, which kind of vanishes easily. But what's also true is that even away from the 0, there are things that are already happening that we don't have any sort of standard explanation for why they're happening. But I think they are the same zeros. I'm not sure if they're just a subset or bigger, that I'm not sure.
There's also some question of how hidden the hidden zeros are from experimentalists who are doomed to work with real momenta and so on.
Yeah.
And the split certainly seems it's in the physical.
Yeah, at least as long as you don't go to sufficiently high point. At 5 points, this is all. At 5 and 6 points, some of the splits are also reachable in physical momenta. Then as you start going to higher points, it starts being a little more complicated.
Maybe I have a question. In the second part, you basically removed this self-intersecting
Yes.
things. Could you think of doing any function in the winding basically? So I rule in, let's say, cursive winding 1 or maybe 2.
Yeah, so these self-intersecting curves, Well, we would not call them windings just because, well, there are literally windings at higher loops. I don't know if that's what you're mentioning, but already here, you can like, so if you keep or like remove them, this is only gonna affect like sort of higher order corrections, so keeping them around or not. So you can look at what's the difference between the higher order corrections. So that's definitely something you can consider. But it is for sure true that at all orders in alpha prime, they will define a unitary kind of completion. The question is whether these integrals where you don't keep all of the curves, so you just throw away some of them, will still be unitary on the massive poles, right, the massless levels, when you factorize on the massive levels. Yeah. Yes?
So since you mentioned this is a theory of colored scalars, are there like separate color factors, or are you working in a large number of colors?
Oh yes, so this is assuming that I'm like fixing the color ordering, so I'm just looking at always some color ordered part of the amplitude. And I can get non-planar contributions, so it's not about large n or anything. Like, so I mean at tree level, when I fix the color ordering, I only get planar diagrams, right? At one loop, then you can sort of have contributions from planar diagrams as well as non-planar. Here, that just corresponds to different surfaces. I just didn't describe that, but we also have surfaces which correspond to having sort of different color factors. For example, this would be sort of a 4-point where I have a sort of trace corresponding to the outside and then a trace corresponding to the internal guys. So yes, I'm just in the same sense, of organizing the sort of topological expansion in this way. So where I'm always factoring out the trace factors if you want. Here I'd have 2 trace factors. At one loop so far, what I drew would be the sort of corrections that would be proportional to n, right? Because I'm assuming that this guy is just giving me n. So at large n, these would be the only ones that would dominate. But I can also describe surfaces that determine these guys as well. I didn't discuss that, but all of this generalizes to those cases.
So splits also generalize?
Yes, actually, sorry, that's a. I will talk about that, like in particular for pions, because it's at least mentioned, is that all of these features about splits. So I did them at tree level, but these are just features about overlapping surfaces. So at loop level, now you can do this in more interesting ways. You can sort of, as long you pick 2 surfaces and then you kind of overlap them on some vertex and then do whatever you want, and then just find these map on the curves. Apply that on the level of the integral as just a consequence of these u variables. It will also definitely generalize to the loop integrands. To make them to generalize into post-loop integration statements, you actually need to sort of combine them with soft limits. So for pions, we can use the splits to derive like sort of multi-soft factors that are there at all orders. So
Can you find things that are 0 that are not obvious?
Yes, so like we can, yes. At tree level, there are a bunch of like zeros that are completely not obvious. At loop level as well, like we can sort of predict the soft factors and then you can make the soft factors vanish. Yes.
Okay, I think we've approached the scheme independent cookie cutoff.